is the detector in the image?
This one?
Yes.
James Clerk Maxwell Telescope,
Okay.
the JCMT.
We are good to go now? Okay, so it's a pleasure to me, well, good afternoon. It's a pleasure to me to introduce Janik Karoly. He's a visitor from the UCL, University of College of London. He works as a postdoc with Kate Patel that we had last year over here visiting us also. We are in this exchange program with the UCL and the AR, making all the exchange, some travels across the Atlantic Ocean, and we have Janik today. He will present some results on the studies of magnetic fields in the ISM that he's been working on. Previously to this postdoc position, he had been doing some research with SOFIA instrument, which is also used for polarization. It was used for polarization at infrared wavelengths in NASA in California, working with V.G. Anderson. And then he moved to the UK and was working his PhD with Ward Thompson, which is also another big guy of the ISM, let's say, and also working with magnetic fields with single dish, right? And he will explain us the difference between single dish and interferometer, which is the link that we are providing here between the UK and Argentina. Okay, so all yours.
Thank you very much for the invitation. I thought, in honor of being in Argentina, that didn't go well.
One moment. Ahora?
No.
There we go, yes. I thought I might translate this, although with Google Translate, so apologies if it's completely incorrect. But I thought I'd read the title of the talk in Espanol. So, Polarimetría de polvo submilímetro iluminando los campos magnéticos de nuestra galaxia desde las nubes moleculares de baja masa hasta el centro galáctico. Sorry if I butchered that. So before we get into magnetic fields, the first question is why star formation? Why should we care about star formation? And I'm going to borrow this from my boss, Kate. As I've heard her sort of explain it in the last couple of talks, and I think it's a really, really key point, which is that stars form, or the process of star formation dictates really the distribution of baryonic matter in our universe. So whether that be in stellar nurseries, in protostars, in stars dying, in galaxies, or in sort of the large scale structure of our universe, all the material there, it comes from and is due to stars. And star formation will also dictate the evolution of galaxies. So in order to understand everything in our universe, we need to start with star formation. You better need to stand over here. There we go. And so the question is, what do we not know about star formation? Now, most of us would say you take a dark ball of gas and dust and you let gravity do its work and you end up with a star. But this is not as efficient as if it was just gravity alone. And the reason why is we know, or we think, that it's gravity fighting versus quite a few things. You have thermal pressure preventing the collapse, you have non-thermal turbulent motions, you have feedback effects, and then you also have magnetic fields. And the magnetic fields themselves, we know they exist. We have them here on Earth, of course, or you can see with the northern lights, and then if this loads, we have them on the sun. But these are magnetic fields on the order of a Gauss or 1,000 Gauss, which is sort of order Tesla. I'm going to be today talking about magnetic fields that are on the order of 10 to the minus 5 to 10 to the minus 3 Gauss, so sort of micro to, or milli to micro Gauss. And this is now the first look of the magnetic field in the ISM. So this is the Planck all-sky survey at 353 gigahertz, so about 850 micron. And the colors there, the orange is where all the dense gas and dust are. And the line, the drapery pattern you see over it, traces the magnetic field orientation. So we know it's prevalent throughout our galaxy. And we also know that it's prevalent throughout the molecular clouds and star-forming regions, with very well-ordered magnetic fields through all the way down to sort of core and clump scales. And so looking now at the importance of magnetic fields in star formation, so it's one of the ingredients, right? But the question for the longest time was, does it even matter? Do we need to care about it? Simulations have done wonderful things for that. So a lot of the magneto-hydrodynamic simulations that have now been able to include the magnetic field demonstrate that there is a role for it. But do acknowledge, of course, it is one ingredient in a soup of molecular cloud and star formation. But it can play some roles consisting of, or playing roles against shock formation, compression, support against gravitational collapse, and some of the highly ordered fields may decrease turbulence decay rate, and turbulence is another thing that might help prevent star formation. So a lot of signs are pointing to magnetic fields in general helping to suppress star formation, although we'll also see a little bit later on it may sometimes help it. This might be a familiar picture for those of you who were with Kate's talk last year. I've shamelessly stolen this from her. But this is sort of our current idea of low mass star formation. So we start out with a molecular cloud. Material will slowly sort of start to fall inward, and we begin to fill these, or form these filaments. And then within those filaments, we form cores. Those prestellar cores will eventually undergo gravitational collapse to form a protostar. And so what I'm here today to talk about is what's the role of the magnetic field in this process? Where do we draw the lines? And so, to just start on the larger scale, so sort of the molecular cloud and the filamentary structure, that's something that the JCMT can help us with. So whether that be nearby star-forming regions or slightly intermediary distance star-forming regions up to sort of a couple kiloparsecs, JCMT can resolve that molecular cloud and filamentary structure. And so our theory for magnetic fields is, so they're in the red here, you have sort of this low density material, ambient material, and the material is preferentially going to fall along the magnetic field lines. So we begin to form these filaments. Sorry. And this is something that we see. So in the low density areas, you would expect the material to be sort of parallel with the magnetic field lines. And then when you actually form these filaments, you're now having a structure that is perpendicular to the magnetic field lines. And this is something that's shown using HROs, histograms of relative orientation, and was shown with Planck and Herschel images, where you're going in low density regions. You have this basically positive means they're parallel. You go from parallel down into perpendicular, and there's a threshold density where this happens. And you can sort of see it in this image up here, where in sort of the lower density area, you have magnetic field parallel, and then when you get down into these high density filaments, you actually have the magnetic field perpendicular. And then what happens within those cores? Well, again, magnetic fields like to, or the material likes to fall along the magnetic fields. And so we then start to condense these cores within the filaments. And so they sort of start to form this oblate shape as the material keeps falling in, and they become very dense until, and then that's where we're reaching this prestellar core. And again, at nearby distances, JCMT, single dish, we're still able to resolve what's happening. But as we move further and further away, and we need higher and higher angular resolution, that's where something like ALMA, an interferometer, becomes very helpful. And so once we reach those densities, this is sort of the ideal image of magnetic fields in star formation, which is that, excuse me, they begin to get pitched. And the reason for this is, I kind of skipped over in the last couple slides about why materials falling along the magnetic field lines. And that's because these molecular clouds, although I'm saying the word molecular and that implies neutral, they are ionized. So they are ionized due to cosmic rays that are able to penetrate into even these high density regions. And in those regions, the column density of ionized, or the volume density of ionized material is still high enough that you have ion neutral collisions, which couples them together. And now the ions are the ones that don't want to cross the magnetic field lines. So when you have these low density regions, and as you're building up your filaments in your cores, you're at densities where the ions are flowing along the magnetic field lines and they're dragging the neutral material with them. But once we get to higher density regions, the idea is this sort of collapses, which is that you're getting so dense that the neutral material, the gravity starts to take over and it's pulling that neutral material inward and dragging with it the magnetic field lines, which are the ions are still feeling the influence from.
Sorry, one question.
Yes.
The ions spiral around the magnetic field lines, or this is a force-free configuration?
That's coming in, yeah.
No.
Oh, yeah.
Yeah.
And so I'm saying this is our ideal picture, so we expect to see it everywhere. We do see it. We have seen it way back in 2006 with Joseph Michael Girard. And we see it in some cores as well, but it's not quite as prevalent as we would expect if this is magnetic regulated star formation. But then the final role that the magnetic field might play is in forming protostars and their outflows. And so up here you have an ideal MHD, so there is none of this sort of dragging magnetic fields inwards, or there's no movement across the field lines, and you generally don't form a disk, and you get really high magnetic field strength, which suppresses disk formation. With non-ideal, where you allow this sort of dragging to happen, you do actually form disks. So the magnetic field is quite an important piece in explaining the disk structures we see in protostars, as well as the orientation of their outflows. And so that was all low mass star formation. Spent about 5 minutes on that one because we have a slightly better grasp on it. And now we move to high mass star formation, and I get to say, we don't really know. We have an idea that it might still sort of follow this path where you have a molecular cloud, you're forming these filament structures, but now these filaments, rather than forming cores or beads along, they're just accreting material down into a central hub. And once that hub gets massive enough, then we don't know. We know there are high mass stars out there, so they need to be formed somehow. This is the most likely environment for them to do it. But do multiple form? Is there competitive accretion that will form just one and some other ones? So this is still a large question, and one that we're actively working to figure out. And so how do we measure the magnetic fields? So I'm going to go through 3 methods that I'm not going to talk about today at all, but just for completeness sake, to show that the way I do it is not the only way. So Zeeman effect, this is kind of the gold standard, but it's very observationally intensive, especially in high density regions. But you get the line of sight magnetic field orientation, and you get to actually measure the strength of the magnetic field. Faraday rotation is something that's often used with extragalactic observations, where a lot of the intervening material will actually rotate the polarization you're observing. And so again, you can get a line of sight strength and direction. This has actually been some work done by Marnoosh Tahani, where she has done a lot of intensive work to figure out sight lines within our own galaxy to try and use this Faraday rotation to actually infer line of sight magnetic field strengths around the Perseus molecular cloud. But this is very complex, and it requires a good characterization of any foreground and background material. Goldreich-Kalliopis effect and velocity gradients both deal more so with velocity. So the Goldreich-Kalliopis effect, it's polarization of molecular lines or molecular transitions, and velocity gradients. It's as it sounds. You're calculating a large-scale velocity gradient, and the large-scale magnetic field is perpendicular to those. So those are Two methods to sort of complement the rest of them. But the one that I'm going to be talking about today, that both ALMA and the JCMT use, is dust polarization, which is that, in a nutshell, dust grains polarize light. Those dust grains are aligned with the magnetic field via something called the radiative alignment torque theory. And from it, we can get the plane of sky magnetic field structure, but not necessarily a direct measure of the strength. And so how does this work? So you have your molecular cloud, which has your classic gas, your H2, CO, but it will also have dust grains. And this isn't dust as we're familiar with on Earth necessarily, but sort of silicates and carbonaceous compounds that are within the molecular cloud. Those dust grains we assume to be irregular. We like to just draw them as little ellipsoids, but they are far more complicated, and the theoreticians who put this together have some of the images in their papers, and yes, they're far more complex, as you might imagine, being silicates and carbon grains. But we take them to be ellipsoidal, and essentially what's happening is you're getting an incident light photon, so you get incident light, which spins up this dust grain. When the dust grain spins, it exchanges some of that energy using the Barnett process, and it gains a magnetic moment, and then this magnetic moment starts to precess around the magnetic field with its minor axis aligned. And once you're hitting this with enough, it sort of averages out, and you get this magnetic or dust grain that's aligned with the magnetic field with the semi-minor axis parallel. And this is actually something that's been shown in labs. So they've spun up dust grains with a laser, and they have observed it as well aligned with the magnetic field. So this is a phenomenon that we know happens and works, and it's tested, or it's cleared a lot of the observational boundaries that have been put on it.
So I don't understand, how do you separate the charges in the
so that's something that it's the I'm gonna say the Barnett process, and feign any knowledge on it other than you're exchanging this spin energy, the angular momentum energy, for then this charge separation. So it's some physics process which I'm less familiar with, but you're essentially inducing this charge separation. So then you get your electric field and then your magnetic moment that's perpendicular to it. Mm-hmm. Yes, I would point you towards looking up the Barnett process, because that's the extent of my knowledge on it. And so we have dust grains aligned with a magnetic field. How do we actually observe it? Absorption polarimetry is when there's a background star, it emits unpolarized light, and then the dust grains will absorb that light. And so then you get maximum transmission along the minor axis of the dust grain, and so that's where the light is polarized, along the minor axis. And since the minor axis we know is aligned with the magnetic field direction, the polarized light we observe, the polarization direction traces the magnetic field direction. But this is in optical and near-infrared wavelengths. In far infrared to submillimeter and millimeter, so ALMA as well, we're now dealing with emission, thermal emission. So now these dust grains are emitting thermally, and they're emitting along their major axis. So that light is polarized along the major axis, and so we actually rotate these polarization vectors by 90 degrees to then get the inferred magnetic field direction. So for the rest of this talk, whenever you see a little line and I'm saying magnetic field, what we've done is we've observed the polarization and just rotated that vector by 90 degrees. Which sounds simple, but it's a lot more complicated. And so James Clerk Maxwell Telescope, so this is the telescope that's been popping up in little pictures on the slides. It sits atop Mauna Kea in Hawaii at about 4,000 meters. It's a 15-meter dish that observes primarily in sub-millimeter. Claim to fame, supposedly, it's still the largest sub-millimeter telescope in the world for the last 30-odd years. We're hoping that telescopes like Atlas come to fruition and kind of beat us, because it would be great for science, but at the moment we're still somehow the largest sub-millimeter telescope. And it benefits from being high up on Mauna Kea, having some of the best observing conditions in the world, not quite as close as the Atacama, I'll hold my hands up, but still quite good, and allows us to observe in the submillimeter. And then this is the instrument that we're actually using. So it's Scuba 2, which is the submillimeter common user bolometer array. So it's a 10,000 pixel bolometer camera that's housed in this blue box right here. It's in dual band, so it's 450 micron and 850 micron. 450, even though we're high up on Mauna Kea, it's not incredibly stable, so it's still very difficult to observe at that wavelength. So most of the stuff I'm going to be presenting is going to be 850 micron. And then it has with it a polarimeter that we call Pol2, that is essentially a half wave plate that gets slotted in front of the camera and measures the incoming polarization. And it does that by splitting up our polarization signal into the Stokes parameters. So Stokes I, which I haven't included on here, is just the total intensity of the light. So it's down here, the polarized intensity, and it's just the square root of the Q squared, U squared, and V squared signal. With JCMT, we are not sensitive enough to detect Stokes V. So we're going to be focusing on Stokes Q and U, where we get our polarized intensity as well as our polarization angle. And so a lot of the work I'm going to be, well, nearly all the work I'm going to be showing you today is part of a large program on the JCMT called BISTRO, which is the B fields in star forming region observations, which was formed to answer the last 20 minutes that I've been talking to you about, which is what is the effect of magnetic fields in forming the filaments, molecular clouds, cores, and down to stars. With the idea that we will use this magnetic field observations to measure and compare the magnetic field contribution versus gravity and turbulence, which we can get from heterodyne instruments and such. And so just briefly about Bistro, so it's actually had 3 generations now. It's been at the JCMT since 2016, I think. So the first project was following up the gold belt objects. The first generation was following up the gold belt objects, which are nearby, sort of moderate mass star forming regions. So your Ophiuchuses, Perseus, Taurus, focusing on them because nearby we can get the highest resolution possible. So we're able to resolve the core and cloud scale magnetic fields. The second generation of Bistro was to start to move towards that intermediate distance. So this is now sort of that 1 to 2 kiloparsec range, where now we're no longer able to resolve the cores. We'll rely on ALMA for that. But now we're able to resolve the large scale magnetic field, especially along sort of these large filamentary structures and much more complicated blobs. And then Bistro 3, we sort of taking the 2 extremes, so now we're coming really, really nearby and looking at the faintest, lowest mass objects, basically just pre-stellar cores on their own without the molecular cloud, and very far away, massive star-forming regions, which is the galactic center. And so, starting with low mass star formation and what Bistro can tell us about that. So this is work that I started in my PhD. Started and finished, which is LINS 43. It's a sub-millimeter bright starless core, which is sort of this area here. And then it also has 2 T-Tauri protostars, RNO 91 and 90, or 90 and 91. 90 is much more evolved now, and RNO 91 is still driving this large-scale CO outflow that seems to have cleared a dust cavity in this sort of broader filament, and the next photo will see that even better. So this is actually a photograph taken by an amateur astronomer, which I came upon after having published the paper, but I thought it was absolutely amazing because it shows you RNO 90 and 91, and actually the RNO is red nebulous object. And then they also are known for having their reflection nebula. And so you see that here, and especially in RNO 91, where you have the central protostar and then it creating a glow in the material around it. But you see this gas and dust here blocking out the background stars. And then this is where that CO outflow comes. And you can see it carving this cavity perfectly in this region, this molecular cloud. And that is key for later. So looking then at the 850 micron dust emission, we were able to get a column density from our dust emission. And one thing we saw was potential fragmentation in the core. This is sort of large scale fragmentation, so you're on 10,000 AU. But what we did is for each of these lobes, so we did it for the central bit and then each of the side lobes, is we calculated their estimated mass from the dust emission as well as their Bonner-Ebert mass. And found that in the main core, that total estimated dust mass is actually much larger than the Bonner-Ebert mass, whereas the two side ones are not. So suggesting that maybe there is some fragmentation going on, and that central dense bit can evolve further. And so the magnetic field and the outflow. This is one of sort of the main ideas in this low mass star forming process is once the protostar is formed and we have this outflow, what's the magnetic field doing? What we found here is a very complicated magnetic field that I sort of split up into an area out here in the tail, the magnetic field in the main dense bit. But then we found this very this distribution of magnetic field direction or orientations that aligned really, really well with the outflow. And when we put it on here again, the idea is that potentially what we're seeing is this outflow has cleared this dust cavity here, and as it has done that, it's reordered the magnetic field. So where you may have had an initial magnetic field that sort of ran along the filament, you now have the outflow that's from the cavity walls has sort of expanded and moved the magnetic field. But in order to try and figure it out, we need to get a good idea of energy, right? If the outflow energy is greater than the magnetic field energy, well, that should probably mean that it has the ability to do that, whereas if the magnetic field energy is significantly stronger, then it might have the ability to constrain the outflow. Because again, we don't want material moving across the magnetic field, so if the outflow is trying to do that, but the magnetic field is strong enough, it can maybe constrain it. And so to do this, I'm going to, again, shamelessly steal from Kate, to discuss the Davis-Chandra-Sekar Fermi method, which is how we measure the magnetic field strength. So we only have plane of sky direction. We don't actually have a measurement of the strength from the telescope. So what we have to do is we essentially scale the magnetic field strength as how well ordered those lines are. Because the idea is you'll have non-thermal motions in the cloud that will be moving the material and sort of moving the magnetic field. And the one way to think of it is like a guitar string, where if you pluck it and you're plucking it with these motions, if you have a very taut string or a very strong string, it's going to snap back into place. And so that's what a strong magnetic field would do, and you're going to keep that uniform string orientation. But if that string is not taut, if it's very loose and you sort of move it, it'll move and it'll sort of stay in that shape. It's not snapping back. And so that's what we're looking for in the magnetic field, is that it should be structured. And then if it's not, we're going to assume that that dispersion in the magnetic field orientation is due to these non-thermal motions. And so figuring out how dispersed they are can give us an idea of the magnetic field strength. We end up with this wonderful classical DCF equation, but this is the key thing. Our velocity, our measurement of non-thermal motion is the line of sight, it's one-dimensional. Our dispersion in magnetic field angle is plane of sky, so now the complete opposite dimension from that. And then our volume density is three-dimensional, which itself is inferred from two-dimensional, and calculating column densities with dust mass and can often carry uncertainties as large as 50%, and we're happy if we're order of magnitude. So it's a very imperfect method, but it's been found to agree somewhat well with actually Zeeman observations, which give you a direct measurement of the magnetic field strength. So it's the best we've got at the moment. And so this is what we then get when we use it. Sorry, it's a bit small. But calculate magnetic field strength in sort of the different regions, and we find that in many of the regions, they're subalfenic, which this is a comparison of magnetic field and non-thermal turbulence, where a value less than 1 means the magnetic field has more influence over the flow of material. Value greater than 1, the non-thermal motions, turbulence is going to be playing a greater role. And so we find sort of slightly subalfenic, transalfenic values. And then the mass to flux ratio is a measurement of the comparison between magnetic field and gravity, where again, a value less than 1 suggests that the magnetic field is enough to support the gravitational collapse, and a value greater than 1 suggests that the magnetic field, that gravity will overwhelm it. The magnetic field flux is no longer large enough to prevent that gravitational collapse. And what we see specifically in this region 2 is supercritical, so much larger than 1, suggesting that the magnetic field may no longer be important in that region, and it might be undergoing gravitational collapse with that fragmentation we had seen earlier would make sense. In terms of then the energies that I discussed, we sort of get similar order of magnitude energies, which again, with our uncertainties, it's very difficult then to say one or the other, which happened. But there's definitely, this isn't the first time that it's been seen where the magnetic field aligns well with the outflows, and then as well as having a reordered magnetic field in the core. And the other thing we saw in this region is sort of an evolutionary gradient, where you have the oldest protostar into the youngest protostar into a core that may eventually collapse to form a star. And then in this direction, this arrow I'm showing is pointing towards an OB association in the Ophiuchus region. And the idea here is that potentially everything I've just told you doesn't matter, and what we're actually seeing is a form of star formation, which is triggered star formation, something that's been hypothesized in the Ophiuchus region due to the influence of that OB association. So moving onwards into sort of into the Taurus molecular cloud region, this is L1495A. And here we have sort of this triangle filament structure that has a bunch of cores along it. And what we looked for was, what is the filament orientation and the magnetic field orientation? Again, with the idea that potentially in star formation, in forming these filaments in these cores, we would have a magnetic field that was parallel with the filaments originally, but then once sort of gravitational contraction had started, maybe it would become parallel, and we're plotting filament minus 90, so we see that in a lot of cases the magnetic field is perpendicular to the filament, except for one little core here, which is core 4, where actually the magnetic field we see is very similar to the large scale field. And this led Derek Ward Thompson, who was my PhD advisor, he had managed to dig out an old theory from Meskel in 1965, which gave sort of a critical column density value, at which point your core becomes matter dominated and not magnetically dominated. And this core sat underneath that column density threshold while the rest of these were above it. And so the idea was that you sort of have this large scale field, gravity starts to twist it and warp it, except in areas which are still low enough in column density that the magnetic field still sees the large scale parent magnetic field. And so this aligned nicely with this theory back from 1965. Those are just a few of the cases, but Bistro in general has a whole plethora of observations that I really can't get through all of them, but I encourage you to go check them out. I think Kate showed some of the results last year, but yeah. So we'll move on to high mass star formation now. And this is now work that I'm visiting Manuel for. This is work with MAGMAR, which is magnetic fields in massive star forming regions. There's an R in there somewhere. And so now we're going to try and answer these question marks using ALMA. And just to bring it back slightly to JCMT and Bistro, again, we're observing with JCMT at these distances in these large mass regions, we're observing the filaments. So you see magnetic fields which are perpendicular to the filaments, which is what we had predicted. And this happens in regions where there's massive star formation going on, as well as in here where you start to have magnetic fields which are perpendicular to filaments further out, allowing accretion onto those subfilaments. And then sort of as they're dragged inwards towards this main filament, the material maybe drags the magnetic field along with it, and you again end up with a magnetic field that's perpendicular to that larger filament. And these are sort of the initial conditions we expect for high mass star formation. But what ALMA is able to do is allow us to get down into the core of these regions. So once the filaments have been formed and you've had all this accretion, you've formed that hub where you're expecting your massive star formation to occur, that's where we can use ALMA to get greater detail. And so this is IRAS 16562 minus 3959. This is a nice Hubble image that shows a very large scale outflow. So there's a massive protostar that's sort of sitting within this dusty area here, inside this dusty core, which is exactly where we get our ALMA observations. So these ALMA observations are band 6, which is right around 1.2 millimeter. So we're still tracing that colder dust material, which are these blue contours shown here. And then this region is blown up here, where we see an extremely complicated magnetic field with ALMA. It might be kind of difficult to see here in person. But we get, there's a large scale outflow, which follows this one that we saw in Hubble, which is this orientation. And we see some areas along the dust where the magnetic field may be aligned with this. And then you have areas like little filaments being formed that again trace this north-south outflow, which is a secondary outflow found in CO. And again, you get a slight magnetic field aligning with that further out. But more interestingly, is you have these 4 sort of core regions.
No.
Or no, I think it's me. There we go. Which show potentially hourglass morphology. So I had said earlier, it's our gold standard, but we've only seen a handful. It appears that in this region where you have these evolved cores, dense evolved cores, we might start to see multiple indications of this pinched magnetic field morphology, which would suggest this sort of magnetically regulated collapse into star formation. And this is now what I get to deal with, having come from purely continuum in a single dish telescope to an interferometer that has like 0.1 kilometer per second velocity resolution and 0.05 arc second spatial resolution. And now we're seeing, this is the region in the whole, and we're seeing all these cores, all the magnetic field, and now getting all these fun spectral lines to play with. And just seeing that each of these cores are also at different evolutionary stages, sort of indicated by the different molecules that appear. You have some methanol showing up in some. You have a nice methyl cyanide ladder, which Manuel and I are slaving away trying to use to get a temperature of this region. But this wealth of data really should allow us to hopefully start getting at this answer where we're now zoomed in on this little box. And now this region, this part of it, we have the magnetic fields. That's from ALMA. We have gravity. We have sort of the dust continuum, which gives us an idea of mass and column density. And we also now have, well, both thermal and non-thermal motions from all these ALMA lines. And we have a massive protostar that's in the middle. And we're beginning to see sort of cores forming, or condensations, if I can be not so direct as cores, but condensations forming, where you might start to get maybe the birth of a cluster or something. So I don't know if I'll get it done by Friday when I leave. My mom and I will definitely do our best to, but this is sort of the next step, and hopefully working towards answering this question of how does high mass star formation proceed. Deep breath for myself and you guys. I think I've given you a lot, and I just want to sort of do a summary and a refresher before we jump into the final bit. Pardon the squiggly lines, those were drawn on a trackpad with the Mac. But this is an idea, a summary of what I've gone over, where the red lines are magnetic fields. And so in low mass star formation, we have this large scale magnetic field, and material will start to collapse along it, sort of forming these filaments. In some areas, the magnetic field might be parallel to those filaments in lower density regions, and then you start to get cores that are forming, and those cores might have different magnetic field orientations like we saw in L1495. And then once you get into your pre-stellar cores, you might start to see sort of this pinching occur, and then you might see a magnetic field that is aligned with outflow orientation like we saw in L43. And as for high mass star formation, I still put question marks, but keep an eye out because again, hopefully this is something we'll be able to answer really soon. And so now we're going to be moving from this lovely 1 to 2 kiloparsec radius around our sun that we might call not quite our local neighborhood, but we're going to move into the galactic center. So this is the final part of the Bistro survey, which was we started nearby low mass, that was L43, L1495, and then we're moving far away and really, really high mass. This is the wonderful meerkat image of the galactic center. Won't actually have anything to do with what I'm talking about, but I think what it highlights is the complexity, the high energy nature, which is that you have supernova remnants everywhere, you have large non-thermal filaments, you of course have the bright Sag star complex, and just really a complicated region. That I'm going to try and simplify for you guys and show you some pretty magnetic field observations that aren't these. These are the large scale magnetic field which was observed with Planck and the ACT, and you do just see sort of this east-west orientation. At higher frequencies, at lower frequencies, you are starting to trace some of that that giant radio arc here. And some of the different emission mechanisms, whereas here you're still sort of tracing the dust emission. I would also be remiss if I didn't mention, I don't dare call them our competitors, but Sophia Hawk Plus, before unfortunately Sophia closed down, they had a legacy survey of the CMZ, and there they have this extremely large scale magnetic field. Here they've had an RGB image with Herschel and the meerkat, as well as this drapery pattern that shows their magnetic field orientation. And so some of the motivation from this work starts with the motion in the central molecular zone. So this was first done in 2011, sort of. It was first seen back in 2004, but Molinari in 2011 using Herschel observations. Noticed quite, well, I say quite pronounced, this figure of 8. You guys, that can be up for debate. I don't know how many of you would have seen that if I didn't draw a line over it. But it was this idea that there was this elliptical orbit of the material in the central molecular zone that when projected on the plane of sky was sort of this tilted figure of 8. And then this is from the most recent Protostars and Planets chapter, and sort of gives you an overview of the central molecular zone and the 3 main sort of orbital models. You have a 2-arm model. This is the Molinari one seen from face down, where you have dust lanes coming in a closed orbit of the material. And this was a 2015 paper, which basically took the 2011 model, refined it, and suggested that it's a bit more of an open orbit into this pretzel shape. Still sort of maintaining that figure of 8 structure on the plane of sky. And this was work done by Croatian, Dale, and Longmore. And so where do we come in? So these are the Stokes IQ and U maps. I choose to show them because we have a very strong signal in Stokes IQ because the galactic center is extremely bright and very high signal to noise. So we actually see Q and U maps that show a very nice signal. And you see a lot of the main molecular clouds in the central molecular zone, Sagittarius B2, the dust ridge, the Brit, Sag A star in there with some of the molecular clouds around it, and Sag C. That's the magnetic field. So we don't see as large a scale as Sophia and Hawk Plus, and we're tracing those dense, massive molecular clouds. But we see extremely ordered magnetic fields throughout the central molecular zone on all these molecular clouds. Very, very low dispersion in all of sort of the main ones around it. With the JCMT beam size, we're sort of at around 0.5 parsec resolution for these molecular clouds, which is similar to what large-scale observations of nearby molecular clouds are. So again, sort of the synergy with ALMA is we're providing the large-scale magnetic field, and ALMA comes in and follows up with then sort of now the cloud and the core scale magnetic field that you might expect to see in these molecular clouds. And this is sort of my favorite one to pick out for that comparison. This is cloud CNF, and this is the Perseus molecular cloud nearby. With Planck at 10 arc-minute resolution, we're at about a parsec. Here we're about 0.5 parsec. But size-wise, this thing's about 3 times as big, but this thing has 10 times more mass. So the density of these clouds in the central molecular zone, they should be forming stars rapidly. But they're not. This is one of the biggest questions of the molecular zone, the center of our galaxy is, you have all this material, why is it not forming stars more readily? And this, I think, is a nice analog where it shows high density compared to the nearby Perseus molecular cloud where there is star formation happening, but there's hardly any happening in here. So there's something we're missing here. Could be just the chaotic nature that I showed you from that meerkat image, supernova remnants, feedback, any manner of things. Could be the magnetic field. We did this looking at sort of magnetic field strengths in each of these clouds. And when we did that, we found potentially a globally important magnetic field where you're now in the milligauss regime. You're getting mass to flux ratios which are quite low and sub-authentic Mach numbers. So in a lot of these molecular clouds with highly ordered magnetic fields, you're getting an important role of the magnetic field, which could then potentially help explain that suppression of star formation. But I introduced you guys to the orbit because this was the main work at the end of my PhD, which I carried out into London to work with Kate. This doesn't show it well at all, but there should be magnetic field vectors on there. But essentially what we wanted to do is take this orbit, and again, calling back to the very beginning of this talk, magnetic field the material should be following the magnetic field, not floating against it. So if we have material moving around the galactic center, we would expect to see a magnetic field that's moving along with it or potentially constraining it. And so this is what we looked for. But first, we wanted to ensure that we're tracing the same material. So we are looking for the highest density material, which is what we're observing with the magnetic field. So we used ammonia, which traces, it's again hard to see on this, but there's black contours on here which show the 850 micron dust emission, and it traces this basically moment zero map of the NH, the ammonia, extremely well. So we wanted to use this gas as our main tracer for the motion of this dense material. This was work that took me forever in my PhD, which was to go pixel by pixel in this data cube and fit these velocity components. And the galactic center is complex, some of them having 4, 5, 6 components. And so then we broke up our material into little clumps because we wanted to try and fit sort of velocity continuous lines, really. So it's fit these splines where now the colored dots down here, each dot shows the centroid of a clump, and the color corresponds to its velocity. And we fit these splines to be velocity coherent. which this is the PV diagram for that, and we compare it with the orbital model from 2015. So you can see spatially, the dashed lines are theirs, ours are the solid. It's a bit different spatially, but in PV space, we're still tracing this continuous material, this continuous velocity space. And so, next thing we want to do, compare it with the magnetic field orientation. So again, I just took then the magnetic field, sort of averaged it in these different clouds along the orbit, plotted the difference, and found that in a lot of cases, the magnetic field, especially on this right side of the CMZ, was well aligned with our gas streams. And one thing we wanted to see was this random? So what we did is we, because we wanted to be aligned in 3D, we took a distribution of 2 vectors, about 1 million sets of 2 vectors, calculated their angle difference in 3D space, projected, and then we took any that were less than 30 degrees, we called that parallel, greater than 30 degrees, called that perpendicular, projected them into 2D, measured again the angle, which is what we would be observing, and built cumulative distribution functions from these distributions, or from these populations, and compared them with the cumulative distribution functions of our observations. We found that in all cases, especially throughout the entire CMZ and on the right side, we found that our distribution was non-random, and especially in the cases of streams A and C aligned very well with this parallel distribution. Stream B was a bit more complicated, where it could have potentially been random, but we also got a p-value from our statistical tests, which indicated it could be drawn from the same population as a 50% parallel, 50% perpendicular. All that done to paint a pretty picture. This could have been this slide all on its own, but this was essentially the hypothesis we ended up with, which is on the right side, where there's not a lot of star formation going on. There's far less dense material. It's a lot calmer. You have a magnetic field which is tracing these continuous velocity streams we see. And on the left side, where you have Sag P2, the dust ridge, a lot of the most of the dense molecular gas in the CMZ, as well as some star formation, you have a magnetic field that may be parallel in some parts, but reoriented to be perpendicular. Question is, do we expect this? The answer is yes. This was recent MHD simulations done of a Milky Way-like galaxy, looking at the CMZ and finding that you are expecting the orbital material to be well aligned, or the orbital motions to be well aligned with the magnetic field, except in areas of high turbulence and star formation where you're getting that deviation from alignment. So simulations show it. So do other galaxies. This is the CMZ of NGC 253, again, synergy with ALMA, if you will. They observed the CMZ and found in starburst regions, starburst pockets, you had perpendicular magnetic fields, and in ambient areas, you had a magnetic field that ran along the plane of the CMZ. The most extreme case was some work that Kate did at M82, where again, this one's incredibly starburst, or it's a massive starburst galaxy. And there you have a magnetic field that is oriented to be perpendicular to the plane, whereas in this case, it's in the dust, in the arms, you get it perpendicular or parallel. So this is the idea of using potentially our own central molecular zone to have predictions about what we expect to see in other galaxies at higher redshifts and higher or different evolutionary stages.
What is the size scale of these images?
This one is, this one is, I mean, you're seeing, this is all of M82 right here, sort of, and there's the spiral arm. So this one is less comparable to us. We're like right in the middle here, but this is about the central, I think it's like 250 to 300 parsecs. Whereas in our galactic center, the bit I showed you was the central 150 to 200 parsecs. Mm-hmm. So with ALMA, in the nearest galaxies, we're able to resolve this structure as well. Whereas in our galaxy, we're able to use something like the JCMT or Sophia. But yeah, here we're just drawing the comparison purely with that large, powerful starburst. And so I leave you there. Summary, magnetic fields, they're everywhere. Theory and simulations both suggest that they have an active role in star formation. And we observe some of these roles across the size, mass, and evolution spectrum, where the magnetic fields can help control the flow in low density environments, but also can support against gravitational collapse in star formation, though they eventually do lose out because we see stars. But even in those cases, it might help with the protostellar outflows and disks forming. And then they can also play a large-scale role in the motions of the central molecular zones and potentially explain the low star formation rates we see there. Thank you. I apologize. I have no concept of time. I have no timer or.
Questions for Janik?
What are the range of the degree of polarization that you measure?
The what?
The range, the lowest or the highest?
Like in percentage or?
Yes, or the value, I don't know.
So in these molecular clouds in the low density regions, sort of the maximum that we're expecting in the ISM is 20% polarization. We get that from Planck.
A lot.
Yes.
Yeah.
That happens in very low density sightlines though.
Yeah.
So you're less likely to have a lot of different maybe magnetic field orientations along the line of sight. But Planck has shown up to about 20%. In these molecular clouds, in the diffuse regions, we'll get up to sort of 10–15%. And then in the dense cores, we're down to 0.5%,
Okay.
something like that.
Thank you.
Yeah.
I guess that turbulence destroys the polarization, right? So can you measure turbulence from your polarization observation?
No, so we still rely then on just classic line tracers for measuring the turbulence in these regions, because we're sort of relying on the turbulence to then help inform the distribution of the magnetic field angles where we're getting that field strength. So we're kind of using that. They're intertwined for sure, but I think it's very difficult then to get the turbulence out of our polarization.
And another question, in the first object you were discussing, the low mass protostar, the outflow seems to be only in one direction. What happens with the bipolar outflow?
There is, so there is a redshifted part. So I did just show that blue shifted part, but the idea is I think it's also heavily inclined, sort of 60–70 degrees or something like that. So we're having that really blue shifted side come to us, but there is a red shifted component as well that I just didn't show. Yeah.
Yeah, maybe I missed it, but in that infinity shape that you have, why did you remove this one?
Yeah, sorry, I didn't explain that. I mean, to be we don't have a lot of signal there, so it's a lot of just diffuse material. And the other thing is, what we needed in order to fit this spline is velocity coherence. And what we ended up having is, you're sort of at 50, you come up to maybe 75, and then drop back down to 50. And so in terms of like a physical, how that would kind of look in the picture, it didn't make sense. So weren't able to. But then the rest of these, it's as you're coming around. So you're going sort of -25, and then you're getting really, really negative as you're coming towards us, and then it's going back to positive as you're moving away. So, yeah.
But the real form is that there is an ellipse that is twist.
Yeah.
And this is the projection.
Yeah, so this is what what this model did is they essentially, they had a potential that they started with. They fit a bunch of ballistic models, so letting something drop in and seeing what it did. And then they used also ammonia observations, but coarser resolution, to fit which model fit velocity data the best. So they were actually able to sort of get a three-dimensional model where they have this top-down view and then also the projected view, whereas we're sort of stuck with just this 2D view that we have. But that's kind of, we do lean slightly on it when we have this sort of picture. So this is very much our idea. We've now sort of come above and using a bit of a bird's eye view and leaning on this open model because there's a lot of confusing velocity stuff that happens here with the idea that there must be some material flowing in behind as well as this other stream in front here.
Okay. We don't have
¿Alguna pregunta, Sharon?
we don't have any more questions. Let's thank Janik.
Okay, thank you very much. Very nice talk. Thank you.